Lesson 11.7 is about powers of binomials. So we're going to learn to expand higher powers of binomials than we've dealt with in the past. So normally we've raised binomials to some pretty low powers, like we've squared or cubed. So we knew if we took something like x plus 2 squared, we would just take x plus 2 times x plus 2 and do all of our distribution. So first, outsides, inners, and last. If we had something like x plus 2 cubed, we'd have x plus 2 times x plus 2 times x plus 2. Again, we would have to do a lot of distribution and combining of like terms. So the question is, when those powers start to get really, really high, is there a better way to do that than having to distribute every single term and combine like terms? The answer is yes, there is. And what we can use is something called Pascal's triangles. So I'm going to read this top thing for you here, and then we'll talk about it a little more. It says Pascal's triangle is an array of numbers showing coefficients of the terms in the expansions of a plus b to the n. Although credited to French mathematician Pascal, the triangular array of numbers appeared in a Chinese document printed in 1303. The binomial theorem was known in Eastern cultures prior to its discovery in Europe. The same mathematics is often discovered and invented by independent researchers at separate times, places, and cultures. Okay, we know this as Pascal's triangles, but maybe not necessarily Pascal was the first guy to think of it. We just heard about it published as his work. So what this triangle actually is all of the coefficients if you expanded a plus b to the n. So think about a plus b to the 0. Anything to the 0 is just 1. The first number in Pascal's triangle is 1. A plus b to the first would be a plus b. So the coefficient of a is 1 and the coefficient of b is 1. So the next row is 1, 1. If we squared it, we would get this answer here. You can see the coefficients are 1, 2, 1. And the next row of Pascal's triangle is 1, 2, 1. And so on and so forth. 1, 3, 3, 1 is 1, 3, 3, 1 over here, etc. So we can use this triangle to help us find all of the coefficients. So let's learn a little bit more about how the triangle is generated. It says the pattern of coefficients suggests the triangular array of numbers called Pascal's triangle. The triangle has ones at the beginning of each row, and each of the other numbers is the sum of the two numbers above it. So that's kind of the important thing here. So if I zoom in, okay, we can see that all of the edges are ones. And then to get the 2, what I did was sum the two numbers above it. 3 we got from summing 2 and 1. 4 from 3 and 1. We got this 10 from the 6 and the 3. The 6 came from the 3 and the 3. So if you just look at all of the numbers above it, you can see where you're getting that sum from. Then you can read that little paragraph down there again. That's basically what we already talked about on the previous slide. Okay, let's practice expanding with Pascal's triangle first. Just with a basic one. I know you can do this distribution yourself, but let's learn the pattern. So the pattern is that we're going to have the coefficients from Pascal's triangle. Since this is to the second power, we're going to look in the second row of Pascal's triangle. The second row of Pascal's triangle goes 1, 2, 1. Oh, I just wrote over my Pascal's triangle, sorry. Let me fix that. Let's move it down here. 1, 2, 1. So that's from that second row there. Okay, now the next pattern that you need to learn is that the powers of the A's will be decreasing and the powers of the B will be increasing. So A will start with this power of 2 and go a squared, a to the first, a to the 0. The B's do the opposite. B starts with 0, then b to the first, and then b squared. And so our final answer is 1a squared b to the 0 is just 1, plus 2ab plus 1b squared. And if you did the distribution by hand, you would verify that this is what you get. But we want to now just follow the pattern for higher powers so that we don't have to think about all of those different distributions. Okay, let's try one more that's kind of just a nice low power here. You could probably do this by hand, but let's use Pascal's triangle. So since it's raised to the third power, I'm going to use the third row of coefficients for Pascal's triangle. So the third row is not this first one. That actually counts as row 0. I'm not sure if I said that yet. Sorry. And then this would be row 1, and then this is row 2, and so row 3 goes 1, 3, 3, 1. So let me write that 1, 3, 3, 1. A's are going to start with the highest power, which is cubed. So we're going to go from cubed to squared to the first to 0. And then B's are going to do the opposite. Start with 0 and count up to 3. And so our final answer then is A cubed plus 3A squared B plus 3AB squared plus B cubed. You could do the distribution by hand and you'll verify that this is the same thing that you'll get. All right, let's try a larger one. So here we have A plus B to the 6th. So we're going to need the 6th row of Pascal's triangle. The 6th row of Pascal's triangle goes 1, 6, 15, 20, and then back down 15, 6, 1. We're going to start with the highest power of A, which is A to the 6th, A to the 5th, A to the 4th, A to the 3rd, A squared, A to the 1st, and A to the 0. And we'll do the opposite for the B's. We'll start with 0, then go to 1, then go to 2, etc. Sorry, this is getting super sloppy. But we're going to end with 6. Now, each of these coefficients are positive, so we're adding between each of these terms. We have positive coefficients. So let me write this all together now nice and neat. So the first one is just A to the 6th, because 1 and B to the 0 are both 1. Then we have 6 A to the 5th B plus 15 A to the 4th B squared plus 20 A cubed B cubed plus 15 A squared B to the 4th plus 6 A B to the 5th plus B to the 6th. And so using those patterns, we were able to find that expansion without having to do all of the distribution and combining of like terms on our own. Okay, so this is the question of, well, what happens when it's not just an A and a B? Well, essentially, you kind of want to do a substitution. Like, let's let A equal just that first term, which is x, and then let's let B equal negative 2y. So that we're still in that form A plus B to the n, which is what we need to be in to use Pascal's triangle and this rule of expansion. So let's just pretend then that right now we're at A plus B to the 7th, and let's do that expansion. So we have the coefficients in the 7th row, which are positive 1, positive 7, positive 21, positive 35, positive 35, and then we go back down, positive 21, positive 7, positive 1. A's start with the highest power, which is the 7th, so A to the 7, A to the 6, A to the 5th, 4th, etc. And B's are going to count up, starting with 0. Okay, but now the difference is we need to substitute in x for all of these A's and negative 2y for all of these B's. So, let's do that. I'm going to go for it here. So for the first term, if I plug in x, for my A, I'm just going to get x to the 7th. I'm not going to bother plugging in anything for B because B to the 0 is just 1. For the next one, though, I'm going to have 7 and then x to the 6th now I have b to the first, which is negative 2y to the first. And I'm just going to keep going through with that. So coefficient of 2, then we'll have x to the fifth and negative 2y squared. Coefficient 35, x to the fourth, negative 2y cubed, plus 35, x cubed, negative 2y to the fourth, plus 21 plus 21. I did that wrong over here too. 21. Here we go. 21, where am I at here? X squared, negative 2y to the fifth, plus 7 times x to the fourth, negative 2y to the sixth. And can I fit the last one in? And then this last one is just going to be plus b to the seventh. So plus negative 2y to the seventh. Just barely made it. Okay. So now let's just do all of this simplification. The first term is x to the seventh. For the second term here, I'm going to take 7 and multiply it by that negative 2. So my new coefficient becomes negative 14, x to the sixth, y to the first. And we just keep on doing that. For the next one, I'm going to have 21 times negative 2 squared. So that's 21 times 4. So that's 84 for my coefficient. X to the fifth. And then the y is also being squared. So that's y squared. And we just want to keep doing that process. So the next one will be 35 times negative 2 cubed. So we'll get negative 280. X to the fourth, y cubed. Then we'll have 560 x cubed y to the fourth minus 672 x squared y to the fifth plus 448 x y to the sixth minus 128 y to the seventh. So it seems like a lot of work, but actually this is saving us so much time and energy from having to do all of the distribution and combining like terms by hand. Okay, that's the basics for this online lesson. We'll do a few more examples in class, but it's just the same process over and over. So go ahead and try lesson 11.7 on Schoology for homework. It's in the chapter 15 folder.